Right now, the default way we run artificial intelligence is by sending every request to a massive general-purpose brain. You ask it to solve complex quantum physics or simply format a date, it powers up the exact same billions of parameters. It is the exact computational equivalent of using a massive 50-ton crane for screw driving a tiny watch screw. A deep reasoning model processes a simple instruction by generating an explicit scratchpad of internal thoughts before reaching the answer. This is the overthinking crisis, a computational surge producing 5 to 50 times more tokens than a standard model requires for the exact same query. Generating those extra tokens requires electricity. When millions of users run trivial, everyday tasks through these heavy models, the power draw scales aggressively. A system built this way burns through its available energy and compute limits quickly, bottlenecking the entire network. To solve this, researchers are deploying small language models, or SLMs. These are compact, highly focused AI agents that require only a fraction of the memory and processing power to run. If we keep using space shuttles to go to the grocery store, global AI infrastructure will stall under its own weight. We need a dynamic routing system that matches the size of the model to the size of the problem. Building that dynamic system starts with grouping our models by how they actually work. We categorize them based on their specific training objectives and inference behaviors, rather than treating them all as interchangeable black boxes. We place our fastest, highly responsive small language models into Cluster A. These are built for rapid-fire decisions that take less than 100 milliseconds. Cluster B contains our reasoning models. These are heavier, token-hungry systems reserved strictly for complex math, coding, and multi-step logic. Then we have Cluster D. These are hyper-specialized models trained for narrow jobs, like formatting an API call or scoring a math output. In fact, they often outperform massive models at these specific tasks, while using a tenth of the parameters. The cognitive controller acts as an air traffic controller. It instantly reads incoming prompts, labels their complexity, and routes them. By enforcing a strict energy budget, it sends 90% of everyday queries down the lightweight path, leaving the massive reasoning brains completely dormant. Triage at the system level allows us to align our computing power directly with the actual difficulty of the task, cutting wasted electricity out of the pipeline. But occasionally, a truly difficult problem does arrive, and the controller kicks it over to the heavy thinkers in Cluster B. The reasoning model decomposes the high-level goal into an ordered sequence of actionable tasks. Once the plan is set, it steps back. The individual subtasks are handed to a specialized action model, like SLM-1B, to execute precise API calls, database queries, and code blocks. In older systems, if a web search failed, the agent would often retry the exact same failed search over and over. Researchers call this the passive orchestrator fallacy, where agents get stuck in unproductive repeating loops. To prevent this, the pipeline uses active scaffolding. It deploys process reward models, which are tiny verifiers that sit alongside the workflow, independently scoring the logic of every single step. When one of these verifiers sees a model run the same failed search 3 times, it flags the loop and forces the agent to formulate a new strategy. It does this on its own, without having to wake up the main reasoning brain. By separating the planning, the execution, and the verification into distinct models, we stop complex workflows from turning into catastrophic energy drains. We have looked at how to route tasks efficiently, but there is still repetitive waste happening at the micro-computational level, right down to the individual tokens. Every time an agent receives a prompt, it must read a set of underlying system instructions. Instead of making the model process those same instructions from scratch for every request, engineers use prefix caching. This animation compares the two approaches. The top bar shows a standard model burning compute to reread the same instruction tokens on every request. The bottom bar computes the memory states for those instructions once, locks them in place, and only processes the new tokens provided by the user. In repetitive agentic loops, maintaining a high cache hit rate eliminates up to 90% of the pre-fill compute cycle, speeding up response times and lowering costs. These optimizations stack on top of each other. We start with hardware-level prompt caching, move up to a strict taxonomy of small language models, introduce a cognitive controller for precise routing, and wrap it in a feedback layer of tiny verifiers. By abandoning the idea of one massive supermodel to solve everything, we build an agile, multi-agent ecosystem. It processes data faster, verifies its own work, and radically lowers the global energy footprint of artificial intelligence.